All right, so in the last section of Chapter 6, Sections 6.8 and 6.9, we'll take a look at empirical and molecular formulas. First, we need to define what an empirical formula is. And an empirical formula is simply the smallest whole number ratio of the types of atoms that are in a compound. So it's not necessarily the specific number of each type of atom that are truly in the molecule, it's just the smallest whole number ratio. And the reason we have an empirical formula is because, as the word empirical implies, it comes from empirical data. So from observations of experiments, data was gathered, and empirical determinations could be made. So it doesn't mean it reflects the actual value, because it may not be whole number values, but it's going to give us a ratio. Now, what's more important to us is actually the molecular formula. The molecular formula is going to be a whole number multiple of the empirical formula, but this is always going to be a whole number ratio. And that, the molecular formula, is what we truly have. Okay, so molecular formulas are real formulas. Those are what we would observe if we could hold a molecule of a particular compound in our hand. Empirical formulas do give us the basic ratio, but they may not always be whole numbers, so they may not be the real formula that we see. Okay, they're just a way to relate the values. So for example, hydrogen peroxide has a molecular formula of H2O2. Now, if we look at it, the simplest ratio of hydrogen to oxygen is simply 1:1. So the empirical formula for hydrogen peroxide would be H1O1, or just HO. That isn't what really exists. We can see that HO, if we really had such a thing, it would probably have a charge. It would be a hydroxide polyatomic ion. It would not have the same properties as hydrogen peroxide, H2O2. So they aren't necessarily the same thing. The empirical formula is the simplest version that we get from looking at data, from gathered data, and we're going to look at some examples of that in a minute. And then the molecular formula is what you would really see if you had that particular molecule in front of you. Now, the molecular formula will always be the empirical formula times some factor n, where n is an integer. It's a whole number. In the case of hydrogen peroxide, n happens to be equal to 2. So why would we ever want an empirical formula? Well, again, we had to start somewhere from gathered experimental data. So for example, early scientists wanted to know, what were the simplest particles of matter that we could get to. So they would try to break down everything they could find. One of the things they discovered was that we could break down water. We could decompose a sample of water using an electrical source. So if we take a battery and we hook it up to a source and we run the electricity from the battery through some electrodes and keep the products separated at those electrodes, it was discovered that at one electrode we could produce oxygen gas, and the other one we could produce hydrogen gas. And if we were able to collect that gas and weigh it, we would see that we would produce, let's say, 3 grams of hydrogen in this particular case and 24 grams of oxygen. Now, you may be looking at the picture and thinking that's backwards. Oh, look, how much more there is in the hydrogen than the oxygen. The hydrogen must weigh more. Well, remember, hydrogen has a smaller molar mass than oxygen, so it takes more of it to get to a particular mass. So this is not in error in the picture at all. We have 3 grams of hydrogen, 24 grams of oxygen. How can we use this empirical data, this data that was gathered from an experiment, to determine what the ratio of hydrogen to oxygen would be? Well, again, in the lab, we can't look at atoms, molecules, we can't look at number of moles. What we can look at is mass. We can weigh the mass. So we want to convert from these masses of elements to the number of moles and to the ratio of these that we have coming from that water as we break it down. All right, so here's how we do this. How many moles of each element, hydrogen and oxygen, are going to be formed during the decomposition of the water that we started with the H2O? So what we're going to do is divide the experimental mass of each element by its molar mass. So in other words, these were the given values, the 3 grams of hydrogen, the 24 grams of oxygen. Okay, we were given those values. And what we want to do is simply convert the number of grams to the number of moles. Okay, so here's my molar mass ratios. Those come from the periodic table. Hydrogen is 1.01, oxygen is 16, and that is the number of grams in a mole of each. Okay, now I want grams to cancel out in each case, so I'm dividing by the number of grams. I'm putting those on the bottom, here and here. And then I have number of moles in the numerator of each of these. So when I work that out, it tells me that in 3 grams of hydrogen, I have 3 moles of hydrogen, and in 24 grams of oxygen, I have 1.5 moles of oxygen. Now it might start making more sense why there was more gas on the hydrogen side than on the oxygen side. If we look at sheer numbers of particles, if we look at the number of moles, there are twice as many moles of hydrogen as there are of oxygen. Okay, or we could put it this way. We could say there are 3 moles of hydrogen for every 1.5 moles of oxygen. It's a 3 to 1.5 ratio. All right, so that's well and good. There's some empirical data that we have, but what does that tell us? 3 moles of hydrogen, 1.5 moles of oxygen. What I'm looking for is the ratio of those things, one to another. So what I can do, I know that those molar ratios, those empirical numbers that I calculated, will still relate to the molar ratio within the formula. It will give me the empirical formula. So what I can do is write what we call a pseudo formula for water. I just go ahead and plug in the values that I found, the number of moles. So I said there were 3 hydrogens for every 3 moles of hydrogen for every 1.5 moles of oxygen. So I'm going to write it as H3O 1.5. All right, so there's my empirical formula. That's my simplest whole number ratio. But I know that I can't have 1.5 atoms of oxygen when I write this formula. Remember, it also has to represent the number of atoms that are in relation to one another. So what I'm going to do is take these, and I had the H3 and the O 1.5. If I divide both of those numbers, remember, when I start dividing through, what I do to one, I have to do to all. So I said if I divide 1.5 by itself, that's going to give me 1. But if I did it here, I have to do it over here as well. So I divided this one by 1.5. 3 divided by 1.5 gives me 2. So hopefully, when I get my empirical data, as I start dividing that out, I get to my simple whole number ratio. So I plug the numbers into my formula, and I find that my molecular formula is H2O. So let's walk through the steps that are required to get an empirical formula from experimental data. This is just to get to the empirical formula. Step number 1. Just write down, or if you need to, calculate as given the masses of each element that you have in the sample of the compound. So if you're given the number of moles already, great, you can follow the steps that we just did. Or if you're given the masses of each element, that's great. But you may not always be given the masses. You might be given a mass percent composition, what we just talked about. So it may tell you that it's 39% this element and 61% of another element. Okay, so assuming a 100-gram sample, you can convert percentages to grams. Okay, and then you can just simply convert that number of grams to the grams of a particular element. All right, so once you have grams, so step number 1, the goal is to get grams of each element. Once you have the grams of each element, you then want to convert each of those to moles. Okay, so you're going to apply molar mass. So here we're trying to go from grams to moles of an element. All right, once we have the number of moles, we're going to write the pseudo formula. So we're just going to take the number of moles we found in step 2 and use them as subscripts in a formula. Now, if those are whole numbers and they're the smallest possible ratio of whole numbers that you can have, then you're good to go. Sometimes the empirical formula is the same as the molecular formula. But if it's not, if your pseudo formula has a decimal in it anywhere, or if there's a way to reduce that ratio in any given way, which the empirical shouldn't be reducible, but if you need to adjust that, then what you're going to do is divide all of the subscripts in the formula by the smallest subscript. So if the smallest one is 1.75, you divide everything by 1.75. All right, now, when you do that, hopefully, after step number 4, you end up with all whole numbers, and again, then you'd be done. But if not, if the subscripts that you get from step 4 are not whole numbers, then what you're going to do is multiply. Now, I know it seems weird, you just divided, now you're going to multiply, but you're not multiplying by the same number you divided by. You're going to multiply the subscripts by some small whole number to get at a whole number subscript. Now, there's going to be a table that's in your book and that we're going to show you that can help with that, but if you can't remember what those numbers are, you can do it through process of elimination. You can just start by saying, okay, I'm going to multiply everything by 2. Does that give me all whole numbers? Yes. You can stop. No. All right, then I'll go back to my original numbers and multiply everything by 3. If that doesn't work, go to 4, and so on and so forth. You can just work your way up. Okay, but there's a particular ratio for that. So after you divide your pseudo formula subscripts by the smallest number of moles, and you still don't have whole numbers, then look to this table right here. Okay, so what is the decimal place you have after your number? So for example, I said your smallest number might be 1.75. Okay, that's indicating a particular ratio. If you have something that's 3 and 1.75, so let's say C3H1.75, and that doesn't really exist, but if it did, then you could say, okay, I know if I multiply C3H1.75, if I multiply everybody by 4, 3 times 4 gives me 12, 1.75 times 4 is going to give me 6. And so it tells me I would have C12H6 as a ratio there. Okay, if it ends in 0.66, I multiply by 3, so on and so forth. You can look for whatever the fraction is here, and then this tells you what multiplier you would use to get to a whole number. And sometimes when you multiply, you don't get a perfect whole number, but you're going to be very close. So instead of 1, you may have 0.999 or 1.01, and that's okay. You can still round that to the whole number. What you don't want to do is take something like 1.3 and round it down to 1, or 1.75. You wouldn't just round it up to 2. All right, so let's run through an example of this. We are told that we have 3.24 grams of titanium. And we're going to let that oxidize. So there's titanium. We're going to let that oxidize with some oxygen. And we get 5.40 grams of the titanium oxide. Okay, now I'm not going to write a formula here because that's what we're trying to figure out. What's the ratio of titanium to oxygen? But 5.4 grams includes both of those elements. All right, now that's all it's telling us. Mass of titanium mass of the metal oxide. From that, what's our empirical formula? Okay, so we've got our given values down here. We're trying to find empirical. So, where do we need to begin? Well, now, if we could get everybody to moles, we'd be in good shape. But the problem is, we can't do that. We can't convert the mass of the metal oxide into moles because we need to know the formula to do that, and that's what we're trying to find. We don't have that. Okay, so let's look at our other piece of information first. We're going to set the 5.4 grams aside for now, and let's focus on the 3.24 grams of titanium in there. And the other thing we could figure out, the mass of the oxide after the sample reacts with oxygen. Well, I went from 3.24 grams to 5.40 grams. How did I increase the mass? The only thing I added was oxygen. So if I take the 5.40 grams that I started with, or I'm sorry, that I ended with the titanium and the oxygen in it, and I subtract the mass of just the titanium that I had, what's left will give me the mass of just the oxygen. So let's take a look at that in a little bit cleaner format. All right, so 5.4 grams minus 3.24 grams tells me that I have 2.16 grams of oxygen. So now I have numbers that I can work with. I've got 3.24 grams of the titanium, 2.16 grams of oxygen. I can convert this to moles because I know molar mass of titanium on the periodic table. I can convert oxygen to moles because, again, I know its formula mass or its atomic mass from the periodic table. So now I can carry out my next step. I can convert those two to moles. Okay, and then once I've converted them to moles, then I can continue on and find the ratio. All right, so just in the interest of showing you that setup, 3.24 grams times the number of grams, let's see, 1 mole of titanium per the number of grams. So if you look on your periodic table, which again, hopefully you have out in front of you, I actually didn't have mine open, it's sitting here, but it's not open. So I find my titanium, and it is number 22 on the periodic table, which has an atomic mass of 47.88. Okay, so that will let you calculate number of moles there. Sorry, that went off the screen. And then 2.116 grams of oxygen. Okay, and then for every 1 mole of oxygen, I have 16.00 grams. So I can work those out and get number of moles. Once I have that number of moles, I can put those into the formula. And I can let that tell me what my empirical formula is going to be. And again, keep in mind, it may not be a whole number ratio. It might be a decimal number. All right, so we pull out our trusty calculator. 3.24 grams of titanium divided by 47.88. So we find that for the titanium, we have 0.06. Yeah, we'll call it 68. Oops. Stayed on the screen a little too long there. And then we take our 2.16 grams of oxygen and we divide by 16, and we find that we have 0.135 moles. So now, if I wanted to write it, it doesn't look really pretty yet, but titanium, 0.068, and then I would have oxygen, 0.135. Okay, that doesn't look very pretty, does it? Let's put a 0 there. Okay, and I don't know why these lines keep disappearing. That doesn't look very good. I want to try to get it to something that looks a little nicer in terms of whole numbers, but you know, I can stop here. That is an empirical formula. That gives me the ratio of titanium to oxygen based on just the molar balance. Now, if I divide both of those by 0.068, because that's my smallest number, okay, so divide this side by 0.068, because I know I have to have at least one atom. That's why I divide by the smallest one. I can't have less than an atom. So if I ratio the smallest one to 1, I should be good to go. Okay, now when I do that, I end up with titanium with just one of them, and then divide 0.135 by 0.068, and I see that I get oxygen. The number, if you look at it, it's 1.985, rounds up to 1.99, or essentially 2. Okay, so now this is my empirical formula right here. And that's all it was asking for. So I could actually stop with that thing that says titanium 0.068, oxygen 0.135. But if I want to know the molecular formula, and I take it that one step further, then I get something that looks a little nicer. I know that I have TiO2. Okay, so this is walking through again. Remember that the whole number ratio is N, and I think I have jumped ahead on my slides. Okay, no, I didn't. So we worked through that one. Let's look at another example now. Okay, so going from information that we're given about empirical formula, molar mass, something like that. Okay, now in this case, what they're telling us is we have a molecule of fructose, and it has an empirical formula. So they're already giving us the empirical formula. They're not making us calculate it here. And the empirical formula is 1 carbon to 2 hydrogens to 1 oxygen, CH2O. And they've given us a molar mass. Okay, so we know for the molecular compound what its molar mass should be. We know how much it should weigh. And we know the molecular formula has to be some whole number multiple. Okay, remember, so we said it was times N value. Has to be some whole number multiple of CH2O. So how can we use these two pieces of information, the empirical formula and the molar mass, to get to the molecular formula? All right, what we need to do first is say, what would be the formula mass, or the molar mass, of the empirical formula? Okay, what if I just looked at CH2O? Okay. What would the mass of that be? So if I took 1 carbon times 12.01 from the periodic table for carbon, plus 2 hydrogens times the 1.01 grams per mole for hydrogen from the periodic table, plus, and they've left it out here, but there's one of them, 1 oxygen times the 16.00 grams per mole of oxygen. Okay, so I have 12, 2, and 16 approximately. I add those up. Just the empirical unit would have a mass of about 30 grams per mole. But I know that the total has to, is more. It's 180 grams per mole. And I know it has to be some multiple of that, a ratio. So if I divide the molecular formula mass by the empirical formula mass, I should get a whole number, okay, which in this case is 6. That is my value of N. So in other words, I need to multiply all of the subscripts in the empirical formula by the value that I found, by 6. So if I take 1 carbon times 6, I end up with 6 carbons. 2 hydrogens times 6, I end up with 12 hydrogens. 1 oxygen times 6, 6 oxygens. So the molecular formula of this fructose that they gave us is C6H12O6. Now note that they're breaking it down into parts, but you may have some examples in the homework where they start you out with mass percent composition, and they ask you to go all the way to a molecular formula with some bits and pieces of information here and there. So just be aware you're going to need to be able to tie all of these pieces together to work those kind of problems. Now I'll try to be sure and break it down into parts for you initially so that you can develop those skills as you go along. There'll be some more homework problems on that, but eventually you do want to be able to tie these all together, because that's how you get from experimental data that you see in the lab to a formula. Now, in general chemistry, again, we're trying to provide you an overview of so many of the concepts and skills that you need in order to actually be an applied scientist. So you may not actually use this information for an example until you get to a little bit higher level labs. But again, these are important skills to develop, because these are skills you'll be using in many different aspects of chemistry as we go along. All right, so let's summarize finding a molecular formula for a compound. Okay, so you'll need the molar mass of the compound. Okay, so that will have to be given to you. If you don't know the molecular formula, they'll have to give you the molar mass. They or I, somebody will have to give that to you. You'll need an empirical formula. Okay, and now it says you'll need the empirical formula molar mass. Okay, they may give you just the empirical formula. You calculate the molar mass based on the empirical formula. Okay, and then you are going to determine N by taking the ratio. Okay, you multiply the empirical formula by this N to get the molecular formula. Okay, so once you found N, multiply the subscripts of the empirical formula by that value to get your molecular formula. All right, so that wraps up Chapter 6, and we will apply this to our lab this week and to our recitation, and then we will get started on Chapter 7. Hopefully we'll get into that at least about halfway before the end of the week.